Good morning. This is Jim Barrowman. I'm here to speak about aerodynamics and of a rocket, particularly stability of a rocket, and give you a little insight into the development and nature of the aerodynamic equations that are available these days for determining your center of pressure and therefore your stability. Going to turn on my charts at this point and share my screen. Hopefully you can see those. Let me know if you cannot. Just send me a chat or a question if you can't see this charts. But let me move forward. The model rocket stability is a very key concept for modeling safely, and that's, as I show here, the key about stability is its safety, but it also, the safety part of that is predictability, that you know where your rocket's going if it's stable as opposed to unstable. The other thing is that the good stable operation leads to good performance. Yeah, we've got a. I'm hoping we have the charts up okay. I'm not getting any response. Well, let's see. Let me put them up and share them. And so we're working on stability for a model rocket that makes it safe, predictable, and improves performance. Now, stability is really the tendency to return to a neutral position, that is the initial position or thereabouts, when it's been disturbed. You disturb a ball inside a bowl, and you can see that it will roll back to the center part of the bowl, and that is stable motion. On the other hand, if you invert the bowl and put the ball on top of that inverted bowl, it's in an unstable condition because when you move it off the center, it will roll off and bounce away. Once it settles down on a flat surface, though, it will be what's called neutrally stable because you move it a ways, and as long as it's perfectly flat, it'll just stay to in the new position. That is neutrally stable. For a rocket, that has to do with relative to the airflow over the rocket. Model rockets are aerodynamically stabilized, and that's because the airflow over the rocket, if it's stable, will tend to bring it back into a neutral position. That is, it'll, as you push it to one side, it will tend to come back and fly into the wind rather than fly all over the place, which is what would happen if it were unstable. And of course, if it was neutrally stable, it would just stay over to one side and have a high angle of attack. Of course, that would be what you would see if you were flying along with the rocket. This is what you would see, as many have seen. If you were watching from the side or from below, you can tell very quickly if your rocket is stable or unstable. The rocket motion is caused, of course, by the thrust opposed by the drag, and of course, it's affected strongly by the weight. And of course, the thrust has got to overcome the weight as well as the drag in order to get good motion. The key thing about these translational forces, of course, even when it's off at an angle to the horizontal or to the vertical, the weight is trying to pull it down. The key is that all these forces act through the center of gravity. The center of gravity of a rocket is a very key concept for model rocketry. Again, all translational forces act through the center of gravity. And that's the center of gravity is basically where there is equal mass on both sides of the center of gravity. I'm going to double check on the slides again. Well, I'm assuming that they're visible. I see no indication of okay, good. Okay, so I do have chat information saying it's looking good. Glad to hear it. Okay, so the mass is equally distributed on both sides of the center of gravity. That's also true in every direction. That is, forward and aft, front and back, or side to side. The CG basically balances right where all the mass appears to be, although the mass is actually distributed around the rocket. The key to this is that the rotation of the rocket, and that's what we're talking about in stability, has to do with the fact that it always rotates about the center of gravity because of that equal mass distribution. If you want to convince yourself of this, I'm showing just a stick here below. If you shake that stick, make it a long one so you can really feel it. If you shake it at the center of gravity, it's going to turn fairly easily. But if you try to shake it from one end or the other, you'll notice very quickly that it doesn't rotate as easily, and that's because you're not equally distributing the mass around the rotation point, which is the center of gravity. So that's a key point to stability. But the other key point, of course, is the fact that we have rockets being stabilized not by the translational forces, but by the rotational forces. Rotational force on a rocket comes about because there is air pressure on the side of the rocket when it's at an angle of attack. And that produces a normal force. And that normal force then takes a look to become a moment because of the moment arm between the center of gravity and the center of pressure, and that's the CP, that little circle there. Okay, that produces an aerodynamic moment when it's stable that tries to bring it back towards the direction of the airflow, so that a good stable moment will very quickly bring your rocket back. A lot of times, if they're not totally stable or they're marginally stable, there's an awful lot of wandering in the process, unfortunately. So the aerodynamic moment on a stable rocket, you can see, happens, you get stability when the center of pressure is behind the center of pressure. And we've all heard that, but you now have some sense of why that is true. On the other hand, if it's unstable, the center of pressure is ahead of the center of gravity, and you can see that the normal force is in fact trying to rotate away from the airflow. And that is definitely an unstable situation, and it's hard to predict where that rocket is going to go. Now, you want to be stable. You don't want to be flying a rocket that's unstable, but you don't want it to be too stable. Again, this is a performance point. The stability of a rocket that is flying in a windy condition, that's what usually induces an angle of attack in the rocket. Other things, of course, are the fact that you might have a misalignment of some kind in your rocket, but mostly it's caused by wind. If you have a stable rocket, of course, the wind will deflect it, but it will also try and get back to the flying into the airflow, which is the higher your speed, of course, the less the wind has an effect. But if you have a highly stable rocket, one like the one on the right, then it's going to have a tendency to fly into the wind more, and you're going to not get as much performance out of your rocket. So that's an important to realize, that you can't make your rocket too stable. The rule of thumb has been for many years to fly with about one nose diameter difference between your center of pressure and your center of gravity. That's a good way to do it. You could probably squeeze that down a little bit if it's a very windy day, or you can by adding or subtracting some mass from the front of your rocket. I don't recommend it, but again, if you're really after performance, you might want to take that chance. But always be very careful that it's in a stable, not an unstable condition. Fortunately, as a rocket flies, it becomes more stable, because as the engine propellant burns, the center of gravity tends to move forward. So that's one of the reasons we want to use launch rods to start our rockets off, so that any wind that's hitting you while you're just getting started can't affect you until you're at a pretty good rate of speed, so you get a good velocity, so you're less affected by the effect of the wind. So you want it to be stable. How do you do that? Well, if you have a design that you've already built, as it's been probably told to many folks, and it is a very effective technique, is you use a swing test by putting capturing it on a string at the center of gravity, and then swinging it on the end of that swing. It's kind of a poor man's wind tunnel, as it were. Of course, this works great for rockets that you've already built. And if you've built one and haven't checked the center of gravity, a good way to check just in case and make sure that it is stable. But on the other hand, if you're trying to design a new rocket, you can't do anything to test it until you've actually got it designed and built. So for unbuilt designs, you have to do two things to make sure it's stable. First of all, determine your center of gravity of your design. That's a case of taking all the various components of the rocket and measuring or determining through the catalog information what the weight of all those various components are: the body tube, the nose cone, the parachute, engine itself, any other body tube components that are in play, and then add them all up and do this is again a moment calculation, where you're calculating the various weights and the moments they will put on the center of gravity, and so you just I always use the tip of the nose cone as a reference point, and you just relate them all to that tip of the nose cone, add them all up, and then divide the distance from the nose cone to the particular component involved, and then divide it by the total weight, and that should give you the center of gravity. To get the center of pressure, there's a couple of ways you can proceed. a classic way is a cardboard cutout. That is basically by making a design and then basically cutting out what would be the silhouette of that model, of the maximum shadow that it would cast, for example, and putting the balancing at the center of the mass of that cutout. And that would give you a crude center of pressure. And that's been used for, was used for many years before we had aerodynamic equations that we could use to get the center of pressure. The problem is that that answer is actually the center of pressure at an angle of attack of 90 degrees. That's when you're going to be flying sideways, which is not really the way you want to fly. So the rocket will definitely be way too stable. And that's one of the reasons why the aerodynamic equations were sought out and developed to take away that conservative nature of the answer. And of course, yeah, they'll be stable, but then that'll be that rocket that flies into the wind and doesn't fly very high. And that's, of course, generally not what we want. We want to get our maximum altitude, good performance. So the aerodynamic equations were pulled together back in the mid to late 60s. And I'll talk a little bit about that later on. They're now published in the Handbook of Model Rocketry, at least the last edition that I've seen. They are also published in a number of reports that are available online. I wrote one for Centuri, and that was published. But there are copies. Last time I looked on, did a Google search. You can get a hold of those. As TIR 33 is the number for that. There's also a TIR 30 by Centuri, which explains a lot of what I'm talking about as far as stability and with rockets today. And that is generally available on the web also. But for those that are computer savvy, and I assume most of you are, both RockSim and OpenRocket use the appropriate stability equations to for any new designs, and I think that's probably the simplest and most straightforward technique to use to get to know it. But if you want to do it by hand, if you want to check and see how the actual computations get done, then those other reports are a good way to determine that. Now, these aerodynamic equations are actually equations that were initially derived for the NASA sounding rocket program when I worked there back in the 60s. Sounding rockets and model rockets are both aerodynamically stabilized. Now, of course, not all rockets are aerodynamically stabilized. There are rockets like the Saturns and the Geminis and most of the large rockets. These are actually controlled rockets that either through usually through thrust vector control, are able to stabilize in spite of aerodynamics, basically, because they get feedback from where they're pointing, and they're actually following a trajectory that's been pre-planned into the rocket, as opposed to just following blindly the airflow. But that's not us. We are, and there have been some attempts to make model rockets of a controlled nature like that, and I think to some extent they've been successful. But 99.9% of our rockets are aerodynamically stabilized, and so that's what I'm dealing with today. Now, the equations were based on a lot of aerodynamic research and engineering done back at the NACA, which was the predecessor to NASA. The NACA worked primarily with aircraft and the aerodynamics and dynamics of airplanes. But the work that was done there is equally applicable to model rockets, with some careful assumptions and making sure that the proper aerodynamic techniques were used. Unfortunately, the equations that were derived for sounding rockets were really too complex to be used without significant computer capability. Now, these days there's a lot more computer capability around than there was in the 60s in general use, and especially for model rocketeers. But of course, with the advent of personal computers and what have you, that's less of a concern. In fact, the key difference between sounding rockets and model rockets is the speed with which they fly. Sounding rockets tend to break the sound barrier. They tend to fly supersonically for most of their flight. And of course, they fly to very high altitudes, typically over 100 to 300,000 feet, and well above the atmosphere. But with the appropriate assumptions, we could make the model rocketry equations simpler and more usable by the model rocketry. The simplifying assumptions were used, and again, the key here is that all these assumptions really apply to the sounding rockets. Many of these assumptions, again, down through number 7, or down to number 7. The key on number 7 is, of course, that we are subsonic in model rocketry, not supersonic. So here we are. We can't use the supersonic analysis, or don't want to use the supersonic analysis. And of course, the steady state, the flow is relatively steady state. That just means that you're not getting a lot of turbulence, and that's kind of a repeat of number 6, but it's a key aspect of all those analyses. So those assumptions were key. One of them things that a lot of people are concerned about is the fact that we stay near 10 degrees, less than 10 degrees, or about 10. That's a rough thing because the normal force does change pretty dramatically as you get out past 10 degrees, and therefore the theoretical assumptions that were used are not really valid at that high a angle of attack. Fortunately, a good stable rocket will stay within that boundary adequately, and so we've been very successful in flying without any problem. Now, there's two key aspects of the theory of aerodynamic theories behind the determining the center of pressure of a rocket. First of all, the equations are derived in terms of aerodynamic coefficients, and I'll explain why that is in a second. The normal force, as you can see on the diagram, is the key to stability, and that depends on a number of things. 3 of them are external factors. These are things that you can't control. I mean, only to the extent that you put in a good-sized rocket engine and that sort of thing. But the fact that the air density, you may be flying from ground level, where the air density is much higher than if you were flying from, say, Denver or up at high altitude. There is actually a difference in air density. The velocity, of course, once you lit that thing off, it's going to fly the velocity pattern that the engine and drag dictate. And of course, then the angle of attack, which will be dictated by how well you've aligned your rocket and also by the wind, as I talked about earlier. So those are not really under your control. But there are two inherent factors that you can control. The size of the rocket, that is how big it is. We have you've seen large versions of model rockets and small versions of model rockets that look exactly the same, but one's just larger than the other. And last but not least, and this is the key to this whole business of aerodynamic coefficients, is that the shape of the rocket is represented by the normal force coefficient relative to the understanding the normal force on a particularly shaped rocket. So by combining all these, you get the normal force equation, which is pretty straightforward. The shape of the rocket times the dynamic pressure. This is the density times the velocity squared. You've heard in the past, I think, that the velocity squared is the way that the air really affects you through velocity. And the combination of density and the velocity squared provides the dynamic pressure. That is the pressure that the rocket feels as it flies through the atmosphere. This affects the drag, this affects the aerodynamic moments, and is a key aspect of aerodynamic flight. You'll notice this 1/2 here. This tends to have people scratching their head. The fact of the matter is that that 1/2 is added into the dynamic pressure component because the results of wind tunnel testing confirm that the effective dynamic pressure is 1/2 of the rho times the velocity squared, and so that is the equation for the dynamic pressure, the value used for dynamic pressure. Then, of course, the angle of attack comes into play, and again, you don't want to get to too high an angle of attack for a lot of reasons. And then the size of the rocket. So you have a larger normal force when you have a larger rocket. A simple concept. And the same thing is true of angle of attack, of course. For the same shape, the larger rocket will react at a greater with a greater force associated with a given angle of attack. Now so the Cn alpha, this is actually the slope of the normal force curve on the rocket with angle of attack, is a key factor that depends on the shape of the rocket. And so that's what we use to calculate the center of pressure. And that is true not only for the normal force, but then obviously once you dealing with the aerodynamic moment instability, it's also true for the aerodynamic moment coefficient. So you will see both of those in the upcoming discussion of nose aerodynamics, nose center of pressure. So the second thing is, of course, fortunately, because we're in a relatively linear region of activity, and that again comes back to the assumption of the less than 10 degrees of angle of attack, that the rocket body can be divided into all its component regions, different shapes and what have you, as you can see to the right side there. And you can calculate each of those separately. And you'll notice if you do that calculation yourself, that's exactly how you go about calculating the center of pressure. Is you relative to the tip of the nose, you find the center of pressure of all the different components. I'll let you in on one of the things that again, low angle of attack, people are not used to the fact that your cylindrical bodies typically do not affect your center of pressure. That's true if the body is stiff and straight. It will have an effect if say you're flying a super rock, one of these great long pieces of spaghetti that people have flown in the past. I've flown a couple myself, and they are exciting. And they're interesting to see how they operate, because you'll find that with a rocket like that, the nose is at a different angle of attack than the fins and other parts of the body. And that's what makes super rocks so much fun, is that they don't really act like a normal model rocket. But you can take these separate results just like you could for a center of gravity, and you combine them into a single value for the center of pressure for the whole rocket. So those are the two key components I want to talk about, and they really beyond that, it's a case of going through some careful analysis, using the results that the NACA folks came together and applying them to rocketry. Now, I want to talk about the nose center of pressure. First of all, because it's very straightforward. Second of all, because we ran into some luck on that. We, as a discipline in flying model rockets, because while the center of pressure of the nose of a rocket can be described very simply, it then becomes a matter of understanding the shape of the nose of the rocket. So let me go through that, and you'll see what I'm talking about. So to get the center of pressure of the rocket, you take the CMA, the moment coefficient, divided by the normal force coefficient. Okay, moment divided by force times the diameter, and that gives you the distance from the tip of the nose cone to the center of pressure. The CM alpha is again the slope of the CM alpha curve at alpha equal to 0. You work with that in a integral equation, and you do the integration, and lo and behold, you'll find that the nose is actually dependent only on the volume of the nose cone. And of course, a conical nose cone will have a different volume than an ogive nose cone or an elliptical nose cone. And so you've got to take that into account. What is the volume? It also turns out that the CN alpha, result of the analysis on the nose of any shape, it turns out, thank heavens, is always essentially 2. That is, the CN alpha of the nose, when you use it in this equation up above here, is 2. My analysis is available if you want to try and dig out why that's true, but fortunately, it's fairly straightforward. So to get the location of the center of pressure of a nose cone, you take the volume divided by the base area of the nose cone and subtract that from the length of the nose cone. So what this says is that this distance is actually from the base of the nose, and in order to relate it to the tip of the nose cone, you have to subtract it from the length of the nose cone. Fairly straightforward, but the volume is the key. You can calculate the area because you know the diameter. That's a number you've put into the process. You know the length for the same reason. So you've determined this will be determined. The volume will be determined by the shape. So you have a conical nose You have ogives, as I talked about before, elliptical. You have, you could be spherical. You could have a spherical nose. All these various nose cone shapes, you have to calculate their volume in order to get the center of pressure. Well, it turns out that for everything except the tangent ogive, which is is used very often on model rockets and sounding rockets too. Actually, it's used on sounding rockets more because of their flight in the supersonic regime. There's a benefit to using that. There's also parabolic nose shapes that are used in that regime as well. But we tend to use ogives, and that's what a lot of the manufacturers make shapes for. But lo and behold, I ran into a little oopsie when I went to look to calculate the volume of the ogive nose. And that's a pretty, where F, this is all a function of F. If you look down here at the bottom, it's the length over diameter. So it's what's called the fineness ratio of the nose cone, length over diameter. Okay, so that this is a function of the volume is a very messy function of the fineness ratio. And as a matter of fact, in order to solve that, to really understand that, of course, I didn't want to put that out and have everybody in the world have to use this kind of a monster. I used a computer to run that real quick. And again, that's the kind of thing that today is no big deal, but back then you had to really delve into computer capabilities. And it turns out that when you do that, this complicated thing turns into what in essence is a linear function. Crazy, but it is. And by using that linear function, you can take all this and crank it down to 0.46, a simple constant, just like for the just for a conical nose cone or for an elliptical nose cone. You can use just a simple constant times the length divided by the diameter to get the center of pressure. So what I note for you though is that most ogives are at an angle that are at a size, at a fineness ratio, well at 2 or above. If you get down here to 1 or in 1/2, you're down into a hemisphere area anyway. So you can use a different set of equations down here anyhow, because you can use the hemispherical center of pressure. But up here, for ogives up as pretty much as far as you want to go, you can use this ogive. So to me, that was a really lucky break, and I sure didn't see it coming. And I just wanted to share the fact that we are all lucky that we do have a way to calculate ogive center of pressures without having to use this monster up top. So here we are. We have the capability to do it. These aerodynamic equations have been proven. They're not just a figment of imagination. They've been compared with sounding rocket wind tunnel data. They've been test flown, and they were test flown as part of my development to make sure that they were okay. By flying a number of test models. One was the Century Javelin, which is kind of what this represents, this picture on the side. And then, of course, since then, over 50 years of flying rockets and thousands of stable model rocket flights that have shown that these equations work just fine. Just a point to note, I was talking earlier about too much stability. Here's your, for a javelin, a model, that particular Centuri model, the center of pressure is just in front of the fins, interestingly enough. And that's with a 3-to-1 ogive on the front, and of course plain cylinders and these trapezoidal fins at the back. And the cardboard cutout method, if you were to use that on this, you'd be putting your center of pressure there, so you can see that you'd be dramatically overstable if you use the cardboard cutout method. So that's the name of that tune. I'm open for questions and answers. The key question to ask yourself is, are you stable? Are your rockets stable? Because stable means safe, means predictable, means good performance. And you really want to know it before you fly it. So I'm open to questions, and I'll take them, I guess, in the order that they showed up. Okay, we're getting there. John Petrakis. Can anyone else hear anything? I see it. Okay, we're making sure we're okay. Okay, I don't see any questions. Looks like folks were able to see the activities. My goodness, I heard from Chaz Russell. How you doing, Chaz? Yeah, spreadsheet works. Okay, well, I didn't have any other real questions. Things seem to be working okay. Thanks, Mark, for letting me know that the things were showing up. I think I'm going to let you guys go. I appreciate your attention, and I'm excited about doing this every year. If they'll still continue. I got a question from Paul Kinzer. Is the CP of secant ogives more similar to that of conical or tangent ogives? I would use the more conservative of those two, which I think is the ogive, the tangent ogive. Secant ogive doesn't flow smoothly into the body of into the cylindrical section of the rocket. So it's okay, but it's not something that I would tend to use, frankly. I would go with a regular ogive. But if you're going to use it, then I would recommend, I never did go try and figure out the secant ogive center of pressure, but my guess is it's pretty close to or would be conservative to use a tangent ogive. If there's no others, I'll stand by in case there are. I'm done a little bit early today, and hopefully you learn a little something from what I had to say. And hopefully anybody who's new at model rocketry will understand better the nature of keeping stability in the forefront of your flight. Okay, questions in the chat. Okay, I'll take a look in chat. Yes, nose has to be a point. Every nose, in essence, is a point because every nose ends up at 0 at the front. But as far as I'm concerned, if it's rounded a little bit, it's not a big deal. Launch lugs and cameras attached. How significant are they? Probably not terribly significant. That's one of the reasons we want to maintain a diameter stability, is to have a little conservatism in the situation, so that things like launch lugs and any protrusions, small protrusions. I'm not sure about cameras. It would depend a whole lot more on how big the protrusion was. But again, give yourself, when you have stuff like that, give yourself a larger static margin, a larger distance between your center of pressure and center of gravity. What does a blunt nose cone? What effect does a blunt nose cone? Okay, again, what I would recommend is a blunt nose cone is basically a sphere, a hemisphere, and hemisphere is trying to visualize it myself. A hemisphere is basically a 1/2. The CP is probably, if you use that chart that I showed you earlier, it's at a 1/2 fineness ratio. But if it's a very small part of the nose cone, that is just rounded off at the tip, it's not a major one. And again, it's a key. Yeah, a long ogive with a rounded nose, not a problem. Not a problem at all. I'll thank for some of the other discussions, other points. How would you address a nose cone shaped like an Honest John rocket? That's basically an ogive with a conical boat tail. So instead of going right into the cylindrical portion, it goes to so you use an ogive nose cone with a conical boat tail immediately behind it. Then that goes into the cylindrical body shape. Okay, so Jason, I think I attempted to answer yours anyway. I think it works well. I've done that before, actually. Does CP shift forward as velocity increases? No. Subsonic versus transonic versus supersonic. Well, that's a good question. Subsonic versus transonic. If you're dealing with that, I wouldn't depend on subsonic being more stable than transonic or supersonic. I'm trying to remember how that curve looks. And I think you actually find that supersonic and transonic are more stable than subsonic. But it's frankly, I'm a little rusty on that, to be honest with you. But I think you'd be okay going to, if you're trying to fly supersonic, if you use the subsonic center of pressure, I think you're going to end up, and not only that, but you'll notice that again, your center of gravity is moving forward. So even if you're not moving the center of pressure much further forward, you're sure moving your center of gravity forward. You're using up an awful lot of rocket propellant that goes supersonic. Stable model rocket, okay, from Frank Liacano. Bob, I'm sorry I didn't have a better answer for you there. Yeah, Frank, yes, exactly right. Frank, that it does scale. Again, it's a function of the shape, which is the CN alpha, not a function of the size, because the size is taken into account by the for example, the normal force coefficient equation includes the diameter of the nose, base diameter of the nose, and so your normal force is higher, but your center of pressure is the same. Yes, winds are definitely a major concern for overstable rockets, as I talked about before, both on the chart about not being too stable, and later on when I talked about showing you what happens to the center of pressure when you use the center of lateral area or the center of the flying sideways center of pressure. Paul, I'm glad you. I see. Paul is saying I can confirm that the astrocam attached high on the side of a nose cone, small rocket, can have a significant effect. So that's a situation where you want a larger, at least give yourself a couple of body diameters stability margin, and I think you'll be okay. But I really don't know how you'd go about computing that, because it's on one side. It's not all the way around. Rather than try and crank out a monster calculation of some kind, which is hard to visualize at this point, because those astrocams do have a good bulge. I would just give yourself a couple, just double your static margin. I think you'll be okay. Paul, did you have a rocket go unstable? And what was your estimate versus how it flew? Any insight there? Not seeing an answer yet. Paul, you may have moved on. Do a swing test. Good point. Yeah. Since you've already built it. Very good. I like it. Noah, I got your question. A slight fin cant actually is not a bad thing. It doesn't hurt to spin a rocket. It actually minimizes the. It tends to keep it going it evens out. Let me put it that way. It evens out the any misalignments or things that would cause you to go off in one direction or the other. It actually kind of averages all that out. So slight fin cant doesn't hurt a thing. Well, Steve, don't know how to answer your question about the reasonable lowest static margin. Again, I guess again, I like the earlier. Ultimately, if you're concerned about it, do a swing test. And as far as I'm concerned, once you've built the rocket, and then you start playing with the center of gravity, you can use that as a means to get yourself an idea of that you're adequately stable. A lower static margin for the second stage. It's really not the velocity that matters; it's the shape of the rocket. So even though you're moving quickly, as I said as I showed, the center of pressure is a function of the shape, not a function of the speed. So if you want to try that, again, I think once you have built a rocket, you can play with it a little bit, and a good swing test will ultimately, if you're trying to squeeze it down to nothing, in order to maximize your or minimize your wind your wind effectiveness or your wind response, I should say, then the combination thereof is reasonable. Okay, short, fat rockets like Big Daddy seem to fly well despite having low stability margins. Again, I don't know what kind of stability margins they have, but it could be the fact that they're slow off the pad, so they're getting a CG movement further forward, so that you're not just dealing with the original center of gravity, and so you get a slightly larger static margin. Hi, Vern. Thanks for your note. That's great. Good. Glad to hear you're with us. That's great. Enjoy the conference. Okay, well, I'm out of here, guys. Thank you very much.